This meeting is being recorded.
Good morning to one and all present here. Today, we are going to present our paper on the topic of design of UAV-based RF transceiver for detecting land fertility. This work was conducted by us as engineering undergraduates at Thapa Institute of Engineering Technology, last Patiala last year. Introduction. India is still an agricultural-based economy. Majority of the workforce engage in some kind of agricultural activities. The system which we are proposing measures the soil's electrical conductivity and moisture content using RF-based time-of-flight approach, with the system being mounted on an unmanned aerial vehicle. The system consists of a Raspberry Pi and a software-defined radio, and utilizes a specially designed sloped Vivaldi corrugated antenna and a Wilkinson power divider to acquire raw data. This data on processing can give us the soil's electrical conductivity and moisture content, which are helpful for agronomists to improve crop yield. Right. The geotag map of this data is very helpful and can help in the domain of precision farming, which is an globally established method for managing agriculture and increasing food production, and in turn help us to manage our food security. Okay. So there have been a lot of related works ranging from soil sampling, soil mapping database, global positioning system, remote sensing, soil electrical conductivity using contact sensors, soil electrical conductivity using non-contact sensor, time domain reflectometry, and ground penetrating radars. Most of the techniques were either manual or remote. The manual techniques are very time and resource intensive, and in general, the remote techniques are unreliable and they offer less reliability and hence are not really that much deployable. System which we propose is mounted on a unmanned aerial vehicle. It can be a quadcopter, it can be a drone, and it consists of 4 units. Right? The focus of our paper is on the first 2 units, the RF transceiver unit and the software defined radio unit. The RF transceiver unit consists of an antenna and a Wilkinson power divider and an amplifier. And yeah, so signal is transmitted and received, and uh, the signal to noise ratio is improved with RF amplifiers to boost the signal strength. The software defined radio unit is the main controller of the RF unit to so that we can set the frequency at which we are emitting the EMM waves, and it is in turn being controlled by a Raspberry Pi based data acquisition and control unit using the block of GNU radio. Now I'm going to hand over to my co-author Harsh Pallav Govind Rao.
So now we will discuss the RF transceiver unit of the system. This unit consists mainly of the corrugated Vivaldi antenna and the Wilkinson power divider. We have gone through several iterations and used tools such as parametric analysis and optimization runs to arrive at the best possible design. As you can see, this is the final design of our slope corrugated Vivaldi antenna. The corrugations in the Vivaldi antenna have been incorporated to enhance its performance at low frequencies, and our results have shown that they help improve both the directivity and the efficiency of the antenna. To feed the antenna and match the impedance from the coaxial feed line to the slot of the Vivaldi antenna, we have used a microstrip step transmission line as shown in the figure. In the initial design process, the Vivaldi antenna's radiation patch is made up of the exponential tapered curve that can be expressed as the following equation. Here, C1 and C2 are the constants, and R is the exponential factor which determines the beam width of the Vivaldi antenna. For the feed path, the microstrip slot line balloon consists of three parts. The first is the circular slot line, which is used to realize impedance matching of the microstrip transmission line and can be equal to the open circuit terminal. The rectangular slot line is used to couple the electromagnetic wave from the microstrip transmission line. The second part is the microstrip transmission line, which is used to realize the impedance matching from 50 ohm microstrip to the 146 ohm slot line. The impedance value of the middle segment respectively is 65 ohm, 73 ohms, and 79 ohm. And the third is the fan-shaped structure, which is used to realize the terminal load matching and can be equal to the grounding terminal. Now next, in terms of design specifications, the antenna has a length of 108 millimeter and a width of about 110 millimeter. The substrate material FR4 has a thickness of 1.6 millimeter, and the metal, which is copper, has a thickness of 0.035 millimeter. The operating frequency of the antenna is between 1 gigahertz and 8.2 gigahertz with an input impedance of 50 ohms. The scattering parameter S11 of the Vivaldi antenna is shown, and it is evident from the figure that the curves remains below minus 10 dB from approximately 1 gigahertz to 8.2 gigahertz, which we can consider as the operating frequency band of the design. Now in the next slide, here we see the Z parameter, which shows the real and imaginary parts of the impedance of the antenna. The real parts of the impedance shades around 50 ohms in the operating frequency band. Now, these towards the right, we have the radiation pattern of the design antenna at our desired frequencies. Next, we will discuss the Wilkinson power divider. Since the Adam Pluto SDR has a single port transmitter and receiver, and thus to achieve dual feed dual polarization, we plan to use power divider. Power divider are passive RF devices used to divide power in any ratio. Wilkinson power divider was chosen in our project as it can be easily fabricated, it is cheap and high performing. It also provides better isolation between the output ports when compared to the T-junction power divider. Now these are the design specification of our power divider. We have 1 to 5 gigahertz of operating frequency, and metal used is copper with substrate as FR4. Next, we have the layout design of our 1:2 Wilkinson power divider. Now next slide shows the circuit's main three S parameter. That is, first is S11, which indicates matching, which is below minus 10 dB from 1 to 5 gigahertz. Next, S21 plot shows the attenuation from input to output, which is around 4 dB. And S23 plots shows that the power divider has a port isolation of around minus 20 dB in the operating frequency.
Okay. Now coming to the software-defined radio, it is the main controller of the RF transceiver unit, and it is being controlled by a Raspberry Pi. The SDR basically sweeps through a range of frequencies for providing a better analysis. The received signal from the RF transceiver is demodulated and passed through a chain of filters, and this in turn is collected by our data acquisition unit, which is the Raspberry Pi itself. ADAL-M Pluto SDR has been selected as the hardware platform because it is easily available and it has a wide variety of device drivers too. Okay. As we know, Raspberry Pi is an ARM-based embedded system. Typically, GNU radios and most of the development platforms are available on x86 general platform computers. To deploy the GNU radio onto our Raspberry Pi, we had to rebuild and recompile every dependencies and then in turn work on GNU radio. This was a hectic process, but eventually we got the work done. And now we are able to use our Raspberry Pi to control the SDR, which is in turn connected to our RF transceiver unit. Okay. So after we were able to do the integration, we worked on the software part, right? How what commands do we give to GNU radio to help it use the RF transceiver unit using SDR, right? So this is a sample block diagram. Here we just set the frequency that we want and some other parameters, right? We have to set the type of signal we want to transmit and how we want the receiver, what kind of modulation we need. And we have also implemented the same on a Python script, which is actually helpful if we want to deploy and make it to a production level product. Okay. Now I'm just going to show you a short demonstration or by sending different kinds of signal and also receiving them. And this was done on our antenna. As we have told, the focus on our project was just on developing these two units and not on the data processing. But on processing this data, we and using tops and rods equation, we expect to get the soil fertility levels by analyzing the soil's electrical conductivity and the moisture pattern. And here is the demonstration. I think I can also speed it up. Okay. Yeah, so here we set the frequency. The first one is the sent signal. The second one is the received signal. And we are just going through different kinds of signals like square, sine wave, and seeing the results. And this is done on a Raspberry Pi platform, on an ARM platform, and we are using the SDR ADAML protocol. Okay, I think, yeah, it's the triangle wave, and yeah. Okay. Conclusion and the future scope of this research work. So, hence, a proof of concept device was prototyped, and we were able to design and integrate the RF transfer unit and the SDI unit and using the Raspberry Pi 2. And the raw data, the future scope is that the raw data can be processed using TOPS and RODS equation and can be used to model soil fertility parameters, right? And further integration of the system with unmanned aerial vehicle would help us to enable agronomists by helping them create a geotag map of the world's soil fertility patterns. The system is scalable in mapping large areas in less time with great accuracies. Further, the system can support quick deployment and has a scope to be commercialized for mass deployment and is better for various applications with low cost and better performance than traditional methods and satellite aircraft-based imagery. And the proof of concept system of this novel system and its scope is discussed. So these are some of the references which we used for our research, and these are us and our current affiliations, and we are glad to present our talk at this prestigious conference. And thank you for all your support. Bye.